All right, let's get into it. There's a new global space race happening right now above our heads. But this isn't about planting flags on the moon. This is about building an entirely new kind of internet. One that uses satellites and the frankly bizarre laws of quantum physics to create something the world has never had before. A communication network that is physically and provably unhackable.
So here's how we're going to break it down today. First, we'll tackle the core problem. What does it even mean to have an unhackable message? Then, we'll look at the quantum leap to space that's making it possible. We'll size up the global race that's heating up, dive into the insane engineering challenges, and finally, look ahead to what it's going to take to build the real quantum internet.
Okay, first things first, let's talk about the problem. We think of our digital world as being limitless, right? But it turns out, when it comes to perfect security, there's a hard physical wall we just can't get past.
And this is the question that's keeping a lot of very smart people up at night. See, all of our encryption today, everything that protects your bank account, your private messages, it's all based on math problems that are just too hard for today's computers to solve. But here's the catch. Powerful quantum computers are coming, and for them, these unbreakable math problems are like simple addition. They could shatter our modern encryption, making every secret we have completely exposed. We need a better lock, one that isn't based on math but on the fundamental laws of physics.
And that lock is called quantum key distribution, or QKD. The secret sauce here is a wild physics rule called the no-cloning theorem. Basically, it says you cannot perfectly copy a quantum particle without changing it. It's kind of like trying to measure the exact properties of a soap bubble. The very moment you touch it to measure it, pop, it's changed forever. So if a hacker tries to eavesdrop on a quantum key, they can't help but disturb it. That disturbance sets off an alarm, and you know you've been watched. The security isn't a promise, it's a physical guarantee. So if QKD is so great, why aren't we just running it over the internet's backbone, our fiber optic cables? Well, this is that physical wall I mentioned. These quantum signals are incredibly fragile. When you send them down a fiber optic cable, they just fizzle out after a couple hundred kilometers. And you can't just boost the signal like we do with normal data, because amplifying it would destroy the delicate quantum information. So what do? You go over the wall. By beaming photons through the almost perfect vacuum of space, satellites can connect continents with minimal signal loss. It's a total game changer.
And that realization that we had to go to space led to a true Sputnik moment for this field. One of those moments that kicks off a revolution. And it was all thanks to one groundbreaking mission.
That mission was China's Messias satellite. Launched in 2016, this thing didn't just prove the theory was right, it absolutely shattered all expectations. In 2017, it performed quantum teleportation, transferring a particle's quantum state over 1,200 kilometers. Incredible. But then, in 2018, it did what many thought was impossible. It created a secure quantum key between China and Austria. We're talking 7,600 kilometers. This was it. This was the moment a global quantum network went from science fiction to an engineering problem.
But there's always a catch, right? That amazing link worked because Messias acted as a trusted relay. Think of it like a cosmic middleman. It would get part of the key from the ground in China, then create a totally new, separate link to send a key to the ground in Austria. It works, but it means you have to have 100% trust in the satellite and whoever controls it. If that satellite gets hacked, the whole link is broken. So while it was a revolutionary first step, it wasn't the final, perfectly secure solution.
And you can bet when one country makes a breakthrough that big, everyone else sits up and pays attention. The success of Messias basically fired the starting gun on a fierce global competition. So who's actually in the race to build this thing?
Well, there are really three major players, and they're all playing the game a little differently. First, you have China and the BRICS nations. They're focused on speed, on rapidly deploying a network based on that Messias model to ensure their own security. Then you have the European Union's EuroQCI. Their plan is to build a hybrid fortress mixing fiber on the ground with satellites in space to lock down the EU's digital sovereignty. And finally, you've got the US approach with DARPA's QuanAD. They're tackling it from a different angle, trying to figure out the really tricky problem of how you weave these brand new quantum links into the massive classical internet we already rely on.
Okay, so having a grand strategy is one thing, but actually building these quantum channels, well, that means you're in for a bare-knuckle brawl with the laws of physics, all from hundreds of kilometers up in space.
One of the first and biggest decisions engineers have to make is this: uplink or downlink? Do you put your photon source on the satellite and beam the quantum bits down to Earth? That's a downlink. It's what Messias did, and the hardware in space is simpler. But you're always limited by the power you have on the satellite. The other option is an uplink. You use a powerful laser on the ground, where you have unlimited power, and shoot the photons up to a complex detector on the satellite. It's way harder to build, but it's the key to creating a truly trustless network with much higher performance.
And the list of challenges is just immense. For starters, Earth's atmosphere is like a shimmering, turbulent lens that can completely scramble your fragile quantum signal. Then there's the pointing. You have to hit a satellite the size of a small car, moving at 17,000 miles an hour with a laser beam from hundreds of kilometers away. It's just an unbelievable targeting problem. And to top it off, there's what they call the wavelength dilemma. Basically, the best light detectors we have for satellites and the best ones we have for ground stations operate at different colors. They speak different languages, which is a major engineering headache.
So with all of those nightmare-inducing challenges, how in the world do you go from these fragile one-off links to a tough, reliable, global quantum internet?
The answer is a piece of technology that is still pretty much on the drawing board, but it's the holy grail of this entire field, the quantum repeater. This device would be able to perform an almost magical trick called entanglement swapping. It's like a quantum switchboard that can take two separate entangled links and stitch them together into one long unbroken connection. The amazing part is, it does this without ever looking at the key itself. This is what finally gets rid of that trusted relay problem for good.
And this is where it starts to sound like straight-up science fiction. Because that entanglement swapping process isn't 100% efficient, it fails sometimes, you need to have a lot of backups running in parallel. Current design suggests that to get one reliable connection, each satellite repeater will need about 20 pairs of quantum memories. These are literally individual atoms trapped in place by lasers, all working in perfect concert. The complexity is just staggering.
So the end goal here isn't to rip out all the fiber optic cables and replace them with satellites. It's to build a seamless hybrid network that uses the best of both worlds. Think of it this way. We'll use fiber for the local roads, connecting everything within a city or region. And then we'll use a constellation of these advanced satellites as the massive intercontinental highways that bridge the oceans and connect the continents.
So that brings us to the roadmap. Where are we on this journey? Well, step one, just proving this was even possible, is done. Check. Machias knocked that one out of the park. We are right now squarely in the middle of step two, developing all the complex hardware and software needed to get these hybrid fiber and satellite systems to work together seamlessly. And step three, well, that's the final frontier. That's engineering those mind-bending quantum repeaters and making them tough enough to survive the harsh environment of space.
Which leaves us with one last profound question to think about. Because this technology isn't just about faster downloads or better security. It could fundamentally reshape everything from global finance and national security to our very concept of privacy. So as this race to a quantum future speeds up, we really have to ask ourselves, what does our world look like when our secrets are protected, not by clever math that can be broken, but by the unbreakable laws of the universe itself?